Before we start, any questions you want to ask? How many have started looking at tutorial 5? Not yet, okay. Okay, one more week, huh? Okay, so if any questions, please send to me. I received, I think, one question from one of you. So normally I wait until I get 2 or 3, then I compile together and then I load the answer up, okay? Okay, today I also updated, I think, the lecture 9 on noise, because I think there was a slight typo, so I've corrected it, okay? You will see it in my answer, student question answer. Yeah, so typo, slide 26 is a slight typo, as you corrected. So today we are on the usual schedule, okay? Usual schedule, this is lecture 10 of part 2, okay? Okay, so today's topic will be on comparators. Before we do that, let's go through very quickly the previous lecture, which we talked about noise. All right, so here are some of the key points. Noise power, sometimes you normalize to a resistor, and normally it's normalized to 1 ohm. And then you can look at noise in the time and frequency domain, okay? So for the time domain, you see what is the average noise power within a certain time window, all right? And then more useful, in the frequency domain, you can see the noise spectral density plot, okay? That means what is the property of the noise over frequency, okay? And then from the noise spectral density plot, to find a noise power, you just integrate over the bandwidth, okay? So very important concept, huh? For noise, in order to calculate noise power, you need to know what is the relevant bandwidth, okay? All right? So if you're given any circuit and you're asked to calculate what's the noise power, you should, from the circuit, first of all, try to know what is the bandwidth that you need to use, okay? All right? So every circuit has a certain bandwidth, and that bandwidth is what you use to calculate the noise power, okay? Okay, and if you take the square root of the noise power, you get the RMS, okay, the root mean square, okay? And also, there could be voltage and current, okay? Noise can be voltage, noise could be current. Okay, then we talk about this important concept of the equivalent noise bandwidth. Okay, what is this equivalent noise bandwidth? Anybody can remember? Okay, pi over 2 for single pole frequency response, single pole. All right, the equivalent rectangular or brick wall bandwidth is pi over 2 times the pole frequency. Okay, and that, how was that derived? Anybody can remember? How did we derive that? How do you derive that? You take the single pole magnitude response, then you square it, okay, because noise power is a square. Then you integrate the total noise power, okay, from DC 0 to infinity. All right. From then you can see expression, and then the pi over 2 comes into the expression. Okay. That means to get the same noise power, you just take the noise spectral density, which is flat, multiply by the equivalent noise bandwidth. Okay. All right. But remember, this pi over 2 is only applicable when it's a single pole. Okay. In one of the slides, you can see that if it's a double pole, triple pole system, the noise equivalent bandwidth is not pi over 2, it's less than pi over 2. Okay? Okay, then when we talk about noise, what are the units that we use for noise? Okay, 3,1 dBm, okay, which is relative to what? 1 milliwatt, okay? All this dB is normally, you need to know what's the relative reference, okay? So dBm is relative to 1 milliwatt, which means to calculate dBm, you need to know the noise power, divide by 1 milliwatt, 10 log, okay? 10 log the ratio of the noise power divided by 1 milliwatt, okay? Then dBc is relative to the carrier power, and dBV you must be given what is the reference voltage, okay? All right? So all this dBx thing is always the quantity you have divided by what is the reference, and then 10 log if it's a power thing, 20 log if it's a voltage or current. Okay? So if I have two noise sources and one of them is 2 times, the power is 2 times the other one, what is the difference in dB? In dBm. Okay, let's say dBm. Okay, I have two noise sources, A and B, and one of them, the power is 2 times the first one. What is the difference between the two powers in dBm? Sorry? 10 log 2, 10 log 2, okay? Okay, that means it's 3 dB, yeah? So in power, in the power form, a doubling of power is 3 dB, okay? In the voltage side, a doubling of voltage is how many dB? 6 dB, because it's 20 log, okay? Voltage is 20 log, okay? All right, okay, so this is something to know, okay? And then we talk about input referred noise, okay? So with a circuit with different noise sources, we can always refer everything back to the input, okay? And why do we do that? Because we want to know what is the effective input noise compared to your signal. Okay, all right. Okay, then we talk about different kind of noise sources. For example, from a resistor, which has thermal noise, and then we talk about this. What is this KTOC noise? Anybody can remember? Sorry. Okay, so this is a noise that is sampled on a capacitor. Okay, it's basically it's sampling noise. All right, sampling noise. Okay. So you see, in a lot of more circuits, we want to do a lot of sampling because you can store things on the capacitor, all right? But when you try to store something on a capacitor, because of the switch or the resistor you use, there's a noise there, okay? So what you sample has a noise voltage or noise power, and this is the KTOC, okay? And then you also saw that for a lot of the BJT, the MOS, and then also the op-amp, okay? All have noise involved, right? So I think up to the previous lecture, all your courses in electronics didn't cover noise, right? So everything was assumed to be noiseless. Okay, the resistor is noiseless. The MOSFET is noiseless. The BJT is noiseless. Everything was assumed to be noiseless up to lecture EE5507, okay, lecture 9 on noise. Okay, so now after this lecture, you must remember that everything has got noise. Okay, so very simple, right? Sometimes, if your professor or your friend asks you, hey, I want to use a very big resistor to reduce the current. Okay, I want to reduce my current, my circuit, so I will use a very big resistor, right? Yes, the current will go down, right? But what is the price you pay? Noise, right? The bigger resistor you put there, the bigger is the 4 kT/R noise. Okay, so there is no free lunch. Okay, all right. Okay, then we talk about how do we do noise estimation or do noise calculation. Okay, so what do? First, we need to find all the different noise sources. Okay, and then we need to compute the contribution at the output of all these different noise sources. Okay, 1, 2, 3, 4, 5, 6. What is the output noise power due to each of these things? Okay, and how do we calculate output noise power? We assume that all the noise contribution is, what is this? Okay, it looks like a praying mantis, man. Okay, we assume that all the noise sources is independent, they're not correlated. Therefore, we can add the noise power. Okay? All right? And then, of course, we need to know the bandwidth when we want to calculate the noise power. Okay? And then we talk very briefly about some circuit techniques to try to reduce the noise. Okay? The simplest way is to, if you can filter, put in a filter, reduce the bandwidth. Okay? But you must put in a low noise filter, obviously, right? Okay? Okay, so now today we will talk about a very useful and simple building block, which is a comparator. Okay? Who knows what a comparator does? What is the function of a comparator? As the name implies, right? Compare. Compare what? Compare what? Okay, in general, you can compare any two things. Okay, you can compare voltage 1 against voltage 2. Okay, yes, if it's a voltage comparator, which is the most common type of comparator. But you can also compare current 1 with current 2, if it's a current comparator, right? But in this lecture, we'll talk mainly on voltage comparator. Okay. Okay, we'll look at what's the characteristic of a comparator. We will talk about how do you implement a comparator. Okay, all right. And we'll talk about two different ways. Okay, one is to use a very high gain amplifier. Your op-amp. Your op-amp has got two inputs, right? And how does the output change the inputs? Anybody? Your op-amp? Op-amp output equals what? Equals A times the input difference, right? Okay? So if the input difference is positive, the output will go very high, right? Towards the supply. If the output is negative, the output will go towards the negative supply of ground. Okay? So that is a comparator actually. Okay? Then the second type of comparator we'll talk about is what we call this regenerative or latch comparator, which actually uses positive feedback. Okay? And we'll see later why this is very useful. Okay? And then the third thing we're going to talk about is a very simple concept called offset cancellation. That means any circuit, for example, amplifier that you build, right? There is an offset. Okay? What is the cause of this offset? Anybody? Any op-amp that you design, there will be an offset. Okay? Why? The question is, why is there an offset? Anybody? Huh? Mismatch. Okay, very good, right? Okay, so hopefully not up to today's lecture, right? In all your previous courses, all right, have you come across this concept of mismatch? Huh? Okay, what is mismatch? What is mismatch? Okay, which means that any two components, right, that in your IC, they are not 100% exactly the same. Okay, all right. Now, when you go and draw a circuit, right, you go and draw a circuit in SPICE or even in your handwritten note, right? You draw two resistors, you draw two transistors. Okay, you assume they are the same. Okay, if I draw R1 equals to 1 kilo ohm, I draw R2 equals to 1 kilo ohm, I assume that they are the same. Correct? All right. But when you actually implement this in a real IC, okay, you have to actually draw a resistor which will be manufactured. Okay? Then you'll find that even you draw exactly the same, all right, after manufacturing you can't measure, they are not the same. Okay? All right? So there will be a slight difference, and this difference is what we call mismatch. Okay? So this is the concept. So mismatch comes about not because you draw wrongly, okay? But it comes about because of the manufacturing process. Okay, how they build the resistor, how we build the MOS, okay, how we actually build the BJT, right? Okay, so because of doping, because of the lithography, everything, there will be some small differences, and this is what I call mismatch. Okay, so therefore, when you build your op-amp or whatever circuit, right, your inputs and your current meter load, everything, right, even you write is the same transistor, okay? M1 and M2, exactly the same, right? The M3 and M4, also you draw exactly the same. Same W, same L, everything, right? When you manufacture it and you come out, there'll be some slight differences. And therefore, when you measure the input of your op-amp, okay, if there's no offset, it means that the threshold is 0, right? When they're equal, all right, the two inputs are equal, right, it's considered 0, right? And then, once I have a slight tilting, okay, of the inputs, I will get output will change depending on the gain, okay? But because there's an offset, it means that now the comparison point is not at 0, okay? It could be at, I don't know, 5 millivolt, 10 millivolt, right? Okay? So now, if there's a 10 millivolt offset in the two inputs, in order for it to be greater to compare, right, I need maybe 15 millivolt, I need 20 millivolt, okay? All right? Okay? So this offset becomes a major limitation in the performance of your comparator now, okay? So for a good comparator, you want the offset to be as small as possible, all right? So one way is that, okay, since there's going to be offset, can we think about how to cancel the offset, all right? Okay, actually today I can go a bit slower, huh? This lecture only 24 slides, okay? So actually I can go slower, okay? Okay, so here what you see is a simple block diagram of a comparator. Okay, it looks exactly like your op-amp, right? 2 input, 1 output, okay? And we just want to compare the difference between these 2 inputs, okay? All right, so the comparator can be used as a decision-making circuit. It can also be used in our ADC as a one-bit quantizer, okay? And can you think of useful circuits where a comparator is used? Can you think of any useful circuit where you use a comparator? You've encountered? Sorry? Switches. Can you explain where comparator uses switches? And what's the function? What's the function here? Okay, so he said roughly, okay. So actually when you power up a circuit, or power up a chip, right, there's normally a circuit that it's called a power on reset, okay? So that means you want your chip to start working when the voltage exceeds a certain level, okay? All right, so inside there'll be a comparator, all right, to check whether your power supply has exceeded a certain voltage, 2 volt or 3 volt, okay? So that's where a comparator is used. Okay, in the SAR ADC, okay, the successive approximation ADC, one of the main blocks is a comparator, okay, because you're checking, right? You're checking for different levels, and how do you know? You check using a comparator, okay? That means is my input higher or lower than this level, all right? I use a comparator, okay? So comparators are very, very, very commonly used, okay? That's why we need to study. Okay, so here is the simple transfer curve of a comparator, all right? Output, and this is the input, so we call this the input, and you can see we're comparing against this threshold level, okay? VR. That means once my input exceeds VR, I want the output to be high, okay? Input less than VR, output is low. Very simple. Okay? High or low. Okay? Now, this is when the VR is 0. Okay? That means you compare against a 0. Right? It's the same thing, right? So this is for if the output can swing plus and minus. Okay? So this could be, I don't know, plus 2 volt, minus 2 volt, okay, depending on what the supply you use, right? Now, if you have a single supply, obviously, you can only go down to ground and to VDD, okay? Right? So nothing too complicated here, huh? Okay, so that was if you have an ideal comparator, ideal, right? Ideal. So what happens if you have a real comparator circuit? Okay, what does it look like? Okay, we'll see a few things, right? First thing we will know is that, like the op-amp we designed, the comparator could have a finite gain. So here, in this case, we assume the gain is infinite. Now the gain is infinite. As long as the input is slightly above the reference, my output goes to high immediately. Okay? Alright? It's like ideal op-amp. Okay? But you know that for real circuit, you cannot get infinite gain. Alright? So it means that there is a finite gain. So this is the gain, the slope. So gain defined to be ratio of output to input. Okay? Right? So there's a finite gain, that means you will have a finite slope. Okay? Which means that if this is the reference level and your input is only slightly higher or slightly lower, because of this finite gain, your comparator cannot give you a 100% decision. Right? Because it will not be either at VDD or ground. Okay? It's somewhere in between. Alright? So, which is, to us, is called uncertain. Right? Because we don't know whether is it high or is it low. Okay? Because our high is defined to be VDD, our low is defined to be ground. Okay? So anything that's in between is a bit uncertain. Okay? Which means in this small region, we cannot resolve whether the input is higher or lower. Okay? This is what we mean. Okay? Alright, so obviously the higher your gain, the smaller this uncertain region is. Okay? Okay, the second property of a real comparator, or a real or non-ideal comparator is what we call offset. Okay, offset. Okay, so because of offset, the switching point is not exactly a VR, but it is shifted by the offset. Okay? So if the comparator has a plus 10 millivolt offset, that means the whole switching point is shifted by 10 millivolt. Okay? Okay. Then we talk about this thing, okay? That there is a slew rate limit. What is slew rate? What is slew rate, anybody? This is a term very commonly used in electronic circuits. What is slew rate? Sorry? Rate of change, okay? Rate of change of what? Of your output, okay? Of your output. Alright? So slew rate basically means that your output cannot change instantaneously, right? Like this. Why? Why? Because how? Okay, so you think, how does the output change? Okay, the output was low, and now let's say output needs to be high. Okay, because the input comparison, right? Input is higher than the reference, right? So the output should go high, right? Okay, how does the output go from low to high? Sorry? You need? Pull up, okay. Okay, but how does the pull up work? You need to charge, right? You need a current to go and charge the output, right? Okay, so as soon as the output is tied to some place where there's a capacitor, right? Okay, so the output to go from low to high, you need current to charge it, right? I equals C dVdt, right? So you need current to charge it. So if you want a very sharp transition, you need a very big current. Okay? So if your current in your circuit is limited, right? I equals C dVdt. dVdt is your slew rate or your rate of change. It's equals to I over C. Okay? Alright? So your output will only be able to change depending on how much current you have. Okay? Alright? So slew rate is basically due to finite charging current. Okay? So in part 1 you will learn about how to design an op-amp. Alright? And then as part of that, you have to design the output current of op-amp. Okay, and that would define what is the slew rate of your op-amp. Okay, right? So this is the slew rate, right? Okay, because slew rate, the output will change in a very finite fashion. Okay, no sharp edges down. Okay, finally, the other good property of a non-ideal comparator, or some non-ideal comparator, is what we call the hysteresis. This concept, hysteresis. Now, what is hysteresis? Anybody? Hysteresis. Have you come across this term, hysteresis? Okay. Okay, you learn something new every day, huh? Okay. So, hysteresis basically is that the circuit has some memory. Okay? So, for example, if initially the output is low, okay? Initially output is low because Vin is less than VR, alright? And then as we slowly increase Vin, right? You will cross VR, and then maybe there's some offset, and then the output will go high, correct? Okay, you see that? Now when you're high, and I start reducing Vin, okay? What will happen? You think that somewhere here it will go down, right? But if the circuit has hysteresis, that means it's got some memory, right? Your input have to go much less before you come down. Okay? So this is the hysteresis cycle. Okay? That means roughly the circuit itself has some built-in memory. Okay? That will cause the two up and down points to be separated. Okay? Sorry? Oh, depends on the circuit. Okay? So you may start to think, okay, what is useful about this? Anybody think? Is there any use for this? Is hysteresis useful? Prevent noise, okay. Okay, so let me put it simple. The hysteresis is useful in a comparator if your input or your reference happen to be noisy. Okay, right? So remember, the input and reference change, and then you see, okay, input is bigger than reference. Okay, then it start to go high. Okay, right? But if each of these signals got some noise, then if the noise is big enough, it may cause the input to trip again, output to trip again. So in this case, you will see your output changing, because the noise make it higher, make it lower, right? So, but if you have hysteresis, and the hysteresis is big enough, okay, you will be able to reject some of this noise. That means your output trip high, and then even though there's some noise, it will not go back low again, because the switching point has shifted due to hysteresis. Okay, so this is one example, right? To what? No, hysteresis is not. Hysteresis is actually. Okay, later on you'll see in the circuit. Okay, you see the circuit. I'll show you the circuit, right? Okay, it's not that all circuit will give you hysteresis. If you want hysteresis, you must design it into your circuit. Okay, all right. Okay, so now we come to this simple question: how will you build a comparator, or how will you implement a comparator? Anybody? Now you know what is the function, right? And what's the transfer curve? How will you actually implement a comparator? Or how will you design a comparator? Sorry? Op-amp, right? You just use the op-amp, right? Yeah, just use the op-amp. Right? Op-amp got two input, one output. Op-amp, if you design properly, got high gain. Okay? So that's correct. So one way is to just use a high gain op-amp as a comparator. Okay, the gain must be high because that determines the uncertainty region, right? Okay? Okay, so first, we go back to see what we want out of a comparator first, right? Okay, we want very high gain because of the uncertainty region. Second thing, we want high speed. That means your comparator must be able to make a comparison fast. Why? Why? Not so slow, not so much the slew rate. Of course, for fast comparison, your slew rate needs to be high. Okay, but in a circuit, you may want to make a few different comparisons or many comparisons. Okay, so you want them one after the other. Okay, so if your comparator is too slow, I have to wait a long time, right? First comparison, then I have to wait. Okay, now I can make the second one, right? So for like a SAR ADC, all this, you need to make many comparisons, right? The faster your comparator is, the faster your ADC can work. Okay? And then of course we want low offset and hysteresis, right? Because these two things, the offset is too high, that means you cannot compare or resolve small inputs. Okay? Okay. So we talk about one way is to just simply use a high gain op-amp, right? So this by now you should know this is a symbol of op-amp with the gain function A of S. This is the transfer curve of the op-amp. Okay? If you have one input at the VR, and then this should be very familiar now. The open loop frequency magnitude of the op-amp. Okay? Single pole, all right? At omega p, and unity gain frequency at omega u, and the DC gain at A0. Okay? So this is the op-amp. Okay, but what is the limitation if we use op-amp as a comparator? All right? Okay, so you want a very high gain, okay, but it means that your bandwidth is very low. Okay, right? Okay, because the op-amp is high gain only for very low frequency, depending on what your pole frequency is. Okay? So if the pole frequency or the bandwidth is low, it means that it's not fast. It's not fast. Okay? Which lecture we talk about setting time? On the lecture on filters, right? We talk about settling time. Right? So you can derive what is the settling time for op-amp with a certain bandwidth. Okay? Right? So your settling time, the smaller the bandwidth or the pole frequency, the longer is the settling time. Okay? So this means that in this case the comparator speed is limited, okay? So you can use this out, op-amp as a comparator, but for only for very low speed application. Alright? Okay, so here is the mathematical derivation of what we mean by settling time. Okay? So basically, if you take your op-amp open loop transfer function A of S, alright, and then you apply an input, which is a unit step. Okay? You all know what's a unit step? What is a unit step input? It means the input basically is just one step, okay? 0 to 1 volt or whatever. Okay? A single step. Okay, that's what you call a unit step. Alright? And then you look at what is the output of your op-amp. Okay? So how do we do that? How do we do that? Well, we can do that in the Laplace domain, okay? Laplace domain, right? So here is your amplifier gain function in the Laplace domain, okay, in terms of S, alright? And so the output in the Laplace domain is transfer function multiplied by the input Laplace, okay? And we know that for a unit step in the time domain, the Laplace is equal to 1 over S, okay? So I take A of S, multiply by 1 over S, I get the output VO of S, alright? And then I take to get back into the time domain, I take the inverse Laplace transform, right? There are a lot of tables to help you do this, okay? All right? You'll find that the output is basically it's a 1 minus exponential function. Okay? So this is the output that's going like this. Right? Okay, your input is like this, a single step. The output cannot be like this, right? Because you have finite bandwidth, finite slew rate, so it will be like this. Okay? And this is the 1 minus e to the power of minus alpha t. Okay? This is the exponential rising. Okay? Actually, this exponential output okay, is not even considering slew rate now. Okay, this is assuming that even your op-amp has infinite slew rate, right? But due to the finite bandwidth, it will still be an exponential settling. Okay, all right. Okay, so because there's an exponential settling, we can define what is the settling time. That means I want to know how long does it take for my output to reach, let's say, 99% of the final value, okay, or 98% of final value, okay? Because for it to reach the 100% of final value will take how long? Infinite, okay, because it's exponential settling, right? It will never get there. It will take infinite time to get there, right? But we can define, okay, whether it's 99%, 98%, whatever, we can define that is the settling time. How long does the output reach 99% of the final value? Okay? So this is all the thing you can calculate, alright? So basically, if you want 1%, you need about 4.6 times. This is what I call a 4.6 time constant. This is what I call a time constant. Okay, for exponential settling, we have this concept of a time constant. Okay? Time constant is this 1 minus e minus t divided by tau. Tau is a time constant. Okay? Alright? So if you want better and better settling, let's say 0.1% instead of 1%, you need more time constant. Okay? Okay, so this first part of exponential settling, okay, we call this actually linear settling. Okay? Now, but in reality now we talk about the finite slew rate. That means there's a finite output current, and this means that you will limit the slope of your output change. Okay? So I'll ask you a simple question, right? For the exponential settling, where is the biggest slope? Where in exponential settling is the slope the highest? At low. Okay, this is a time domain now. Time domain. Okay, time domain. Time domain. Time 0 is where the step is. Time infinity is the final value. So now that you know the output goes 0, hit time 0, then it start to exponential come up. So where is the biggest slope? Is it at large time or is it a small time? Small time, right? Right. So very simple, you know this is a VR of t, right? You just take dVR of dt, right? You will find the slope, and the slope is biggest when t equals 0. Okay, right? Okay, and then very simple. We can compare that with this expression. That means we know due to the finite current what is the slew rate of my op-amp, and then I check, is this slew rate bigger than the maximum slope or not? Okay? If the slew rate is less than the maximum slope, that means I'm not going to get a pure exponential settling, right? Because my circuit cannot support this. I mean, my circuit can only go as fast as my slew rate until the slew rate exceed the slope of the exponential settling. Then it will catch up. Okay? Okay. So that was for the first idea, right? Let's use the op-amp as a comparator. So now we come to a different way to implement, all right? What we call regenerative or latch, or some people call positive feedback comparator. Okay? So a little bit of history. Where did this come from? Okay? Actually, it came basically from just a PhD student. Okay? Right? So the PhD student, okay, the professor asked him, okay, can you go and design this circuit, all this, right? Oh, by the way, this circuit, we need a fast comparator, a high-speed comparator. Right? So then the PhD student asked himself some questions, right? What is the function of a comparator? All right? And what is limiting the speed? And how can I make it faster? Okay, simple question, right? If you are the student, you also ask the same question, right? Okay? So now, imagine, so you say, oh, okay, one idea is to use op-amp, right? Op-amp as my comparator. If I use op-amp as my comparator, I want to make it faster, what do I need to do? What must I do? How to make my op-amp comparator faster? I need to make either the bandwidth, okay, bandwidth wider, and then once my bandwidth becomes wide enough, then I need to find, my output current needs to be bigger also, right? Because it needs to rise very fast, all right? So very soon you'll come to the conclusion that you need to add more power, right? I need to burn more power to make my op-amp comparator faster, okay? So then this PhD student said, oh, okay. But that may not be a good idea because my professor said I cannot increase the power too much. Okay? So then this PhD student begin to think, right? You go back to first principle. Alright? What is the purpose of a comparator? Just to make a comparison and compare fast. Okay? That means my slope don't have to be linear. Okay? My gain don't have to be linear. Right? I just want it to be gain to be big so that my speed is fast. Okay? So how can you implement that? Okay, so then he's come to the idea that, well, why don't I use positive feedback? Okay, why don't I use positive feedback? Okay? Alright? That means, how does positive feedback work? Anybody? How does positive feedback work? Previously we talked about negative feedback, right? Filter negative feedback. Okay, now we rearrange our brain and we think, okay, what is positive feedback and how does positive feedback work? Right? So it means that if I have a small change, right, and there's positive feedback, the positive feedback will make the change even bigger, right? So that it will just latch and lock into place. Okay? So initially, everything is flat like this. If there's more change like this, positive feedback will make it like this, right? If it's like this, positive feedback will make it like this, right? So it will very quickly snap the thing to the output rail, okay? Which is what you want for a high-speed comparator, okay? So if you go and read the papers, this is exactly what happened, right? I don't know when was this? Must be, I think 1980s, PhD student came out with this concept, alright? Okay? So, what does the circuit look like, okay? So basically you have a few different blocks, okay? The first block is what we call a preamplifier, okay, a preamplifier. So it's like a little bit like your op-amp, okay? It has some gain, it will just amplify the input difference, okay? But I don't need the thing to amplify all the way to the power supply, high or low, okay? I just need to amplify to a certain extent, okay? And then my positive feedback or the regenerative circuit will kick in. Once the difference is big enough, the positive feedback will come in and bring it to the, very quickly, right? Snap it to the high and low. Okay, all right, and this is where most of the speed improvement come from, okay. right? And then, okay, this last one is just a buffer if you need to try something, okay? So now, what do we mean by, how does a positive feedback circuit look from a concept point of view, okay? So that means, let's say I have two outputs, Vx and Vy, and I have two amplifying blocks like this, placed, one transposed to the other, okay? So what will happen, right? Any change here will get amplified here. Any change here will get amplified back here. Okay? Right? So a very small input will get amplified. Right? And then once it gets amplified, it will feed back again. Right? Okay? So this is one example of a simple regenerative latch circuit. Okay, let's take a close look at this circuit. Have you ever seen this type of circuit before? Okay. Okay, so basically we have two transistors. We'll call them M1 and M2. Okay, connected this way, right? Okay, M1, M2. There's two resistor loads and a capacitor also. Okay, resistive capacitive load like this. And then I connect the output of this M2 back to the input of M1 and connect the output of M1 to the input of M2. Okay? So now what will happen to this circuit? Okay? So we just imagine what happened, right? If this voltage goes up a bit, okay? What will happen? This voltage goes up a bit, it means that M1 will get turned on more, right? Okay, which means that M1 will want to pull this output lower. Okay. Now, if this goes lower, that means M2 will want to turn off a bit more, which means that this voltage can go higher. Okay, and then the whole thing is a positive feedback cycle. Okay, right? Okay. So this kind of a cross-coupled MOS structure is very often is a positive feedback circuit. Okay, a small change on one side will get amplified on the other side, and this change on the other side will amplify whatever was the original change in the first side. Okay, all right. So this is positive feedback. Okay. Yeah. Going to? Yeah, you just go to the supply lah. You cannot. It's limited by the supply, right? You cannot go higher than supply. Okay, all right. You just go to supply and to ground, right? Okay, you cannot go to infinity, right? Because you have no power source at infinity. Okay. Okay. Okay, so for those of you who are interested in the mathematics analysis, you can analyze it this way. Okay? Alright, so here are your two outputs, Vx and Vy. Let's say here, Vx and Vy. Right? Okay? And then here is the load capacitance, here is the residual capacitance. And then your two MOS, you can model the output as a current source, okay, which is GM times the input VGS, okay. So small signal model, you all know, right? Small signal model, you all know, right? Small signal model, okay. So here is an approximate small signal model, right? So you basically have you can write out the equations, all right? Right? And then basically what you'll get is that you'll get a differential equation, okay? And then you can take the integral and you'll find that the output change basically is exponential, okay? It's exponential, right? So you see from a time domain, right? Time versus change in the two outputs, okay? So if the output was slightly positive in the beginning, then with this exponential, you will exponentially increase until you hit the supply. Okay? If the output was slightly negative in the beginning, it will exponentially drop to the low state. Okay? Right? So how do we get to this? We use the preamplifier to amplify to get to the initial imbalance point. Okay? Okay. Now, what is some limitation of this kind of a positive feedback circuit? Okay. Now we know that for the positive feedback regenerative latch circuit, is an exponential kind of response, right, to the plus and minus. Okay. And this thing will depend on what's the initial difference. Okay, the exponential will depend on the initial difference. So, even though it's exponential, if the initial difference is very small, what will happen? What will happen? It will take a longer time, right, to finally get to the end. Okay? The bigger the difference, the faster the exponential will reach the VDD and ground. The smaller the difference, the longer time it will take. Right? So, there's a situation whereby if the input difference is too small, it will need a very long time to get to the final output. Right? And if this time is longer than your comparison time, okay, you have a problem now. Right? Because it hasn't settled yet. Right? So this is what we call the meta-stability problem. Right? That means this regenerative comparator cannot give you an answer, right, in the time that you want. Okay? So let's say you use this comparator in a SAR ADC, and the SAR ADC clock is running at 10 megahertz. Okay, that means every 10 megahertz clock cycle, I want to make one comparison, right, and get the result. Okay, then I do the second and third one. That means 10 megahertz means what's the time? 0.1 microsecond, right? 0.1 microsecond or 100 nanosecond, right? That means after 100 nanosecond, I look at the comparator output, I can't tell whether it's 0 or 1. Okay, that means I have a meta-stability problem. Okay? Which means that the input to this regenerative comparator is too small. Right? So it's taking too long for it to make a final decision. Okay? So this is what I call meta-stability. Okay? Alright? So how to avoid meta-stability? Okay, one simple way, of course, okay, make my time longer lah. Right? If you cannot compare and decide in 100 nanosecond, I give you 1 microsecond. It means I have to slow down my whole system. Alright? Or what I can do is, how about I try to increase what is the initial difference? Okay, remember, the bigger it is, the faster my latch can work. Okay? How to increase? Okay, I add a preamplifier. Right? That means my initial input, I amplify a bit more. Right? Before I give it to the positive feedback circuit. Okay? Or I put a cascade of these kind of things. Right? My first one cannot go all the way to 100%. I put a second one. Right? So the first one only go to, let's say, 50%. My second one will go all the way to 100%. Okay? Right? So use a cascade. Okay? And then the other way, of course, is to, what is limiting my exponential response time is also my load capacitor. My load capacitor. Okay? Right? See, the time of the latch, there's a CL there. Okay, it's obvious, right? If I have a bigger capacitor at the load, I need more time to charge it. Right? Okay? So if I make CL smaller, all right, or make the current or GM bigger, I can also speed it up. Okay? Okay, so here is one example, right? You see, previously we saw the previous circuit here in slide 9, just 2 NMOS cross-coupled, right? Okay, in slide 9, right? Now you see in slide 11, not only 2 NMOS cross-coupled, I add 2 PMOS cross-coupled on top of it. Okay, so now I've got 2 positive feedback hooking together, which means that it should be faster, right? It should be faster. Okay? Okay, so if you do some first order analysis, all right, basically you find that the CL over GM is equal to delta L squared, 4L squared divided by mu times the overdrive. Okay? Okay, so to make CL over GM as small as possible, which means to lower the settling time or to increase the speed, if L can be smaller, I will get a speed increase. Okay? So L can always be smaller because with each technology generation, L is smaller. Right? L is now, I don't know what, TSMC is how much L? 4 nanometer, is it? Or 5 nanometer, or 7 nanometers production. Right? The next generation, it will be 4 nanometers or whatever, right? So with each technology generation, the L is getting smaller. That's why automatically the circuit is getting faster. You see? So for many, many years, the designers are very, very lazy, have a good life. Okay? I want to make my circuit faster. I just wait until the next technology node come up. It'll be faster. Okay? Right? But now cannot. Now because the technology improvement is getting less and less. Right? So the designer now need to use his brain to see how can I make my circuit faster. Right? Even if L doesn't change. Okay? Okay. The other interesting thing about this positive feedback circuit is that there's something which you call a kickback. A kickback. Alright? What is this kickback? The kickback basically is because the output is being snapped by positive feedback, right? Into a very fast kind of exponential transition. It means that there's a danger that this transition can couple back to the input. Okay? Can couple back to the input through any parasitic capacitance or whatever. Okay? Right? It's like a clock feed through kind of noise. Okay? Clock feed through is that your clock is moving very fast and then it get coupled into your circuit through a capacitance. Okay? This kickback is opposite. Your output is changing very fast and you can kick back into your input. Okay? Right? So here you see, right? The rate is the kickback. Okay? As the latch circuit output is changing very fast, okay? If there's any capacitive path, you couple back to the input. Okay? Because your input, we assume, has some finite impedance or this. Okay? Alright? Of course, if you simulation, you just put an ideal voltage source there. Of course, you don't see any kickback. Ideal voltage source is 0 impedance. Right? Okay? Okay, here is that if you have a preamplifier, it can help to reduce this kickback effect. Okay? Right? So you can see here, right? This is a positive feedback. Even if kickback something, if you have a preamp, because of the preamp gain, the effective kickback disturbance at the input is reduced. Okay? And this circuit also acts to isolate the kickback point to the input. Okay? Okay, so let's look at this. Alright, one example. Okay, example. Alright. We have an op-amp. Okay, we're using an op-amp as a comparator. Okay, with a pole frequency. Alright. And we are given that the unity gain bandwidth is 100 megahertz. Okay, that means when the magnitude drops to 1 or 0 dB is at 100 megahertz. Okay? Right? And then there's a DC open loop gain of 80 dB. Okay? Now once I give you the unity gain bandwidth and the DC gain 80 dB, you have everything you need to define the single pole amplifier gain magnetic function already. Okay? Alright? Okay? Okay, because once you know this, you can work out what is the pole frequency. Okay? Because from the unity gain bandwidth. Okay? That means this gain multiplied by this pole frequency is equal to this gain, which is 1, multiplied by this frequency. Okay? Alright? So you see A0 multiplied by this omega 3 dB is equal to 1 times omega u, unity gain. Okay? Alright? Okay? So from here you can see that the 3 dB is at 10 kilohertz, the pole is at 10 kilohertz. Okay? Okay, and then once you know that the is at 10 kilohertz, then we can work out what is the settling time. Okay, based on 0.1% settling. Remember earlier slide we derived the settling time constant for different settling accuracy. Okay, so for 0.1% you need about 6.9 time constant of settling. Okay, all right. So do you know what is the pole frequency? And so therefore 1 over that is the time constant, and we need 6.9. Okay, therefore the settling time to 0.1% is 110 microsecond. Okay, all right. Okay, so that was the settling time for open loop. Okay, now what about closed loop? Okay, that means now I use this op-amp in a closed loop with a closed loop gain of 40 dB here, 40 dB, right? So once my closed loop gain is 40 dB, my effective closed loop pole also change. Okay, from 10 kilohertz it will change to 1 megahertz. Okay, so you look at this as similar to another op-amp with 40 dB gain. Okay, same 100 unity gain frequency 100 megahertz, but now your pole has shifted out to 1 megahertz, and therefore your settling time is much less. Okay. Okay, make sure you all understand what is going on here. Okay. Firstly, the settling time depends on the settling time, if it's true linear or exponential settling, depends on the pole bandwidth, pole frequency of the amplifier system. Okay? Right? Because once you know the pole frequency, you know what is the settling time constant. Right? And depending on the settling time accuracy you need, okay, you need different kind of settling time constant. Right? Therefore, you can calculate. Alright? Okay? So here example, open loop, you have one settling time constant at here. Closed loop, you have another one here. Okay? Okay. So here is one example of a positive feedback comparator. Okay? Let's see what is going on here. Okay? Okay, so very simple. When you're faced with this kind of a circuit, how do you start to understand? How do you start to analyze? How? If your professor or your boss tomorrow give you a circuit and ask you, hey, what is this circuit doing? How will you start? Huh? Sorry? From the input side. Where's the input? This side, is it? V in, okay. Okay, first advice is that, you always look at where the input, where the output. Okay? And this is very important, when you draw your schematic, please draw it in a logical way. That means input come from the left, okay? Output go to the right, right? Or input come from the top, output come from the bottom. Okay, there must be a certain structure. You don't go and mix your circuit, input left, right, up, down, all right? Make it very hard to read your circuit. Okay, all right? So most people, when the good discipline is input always on the left, output always to the right. All other control signal, all right, top and bottom. Power supply always come from the top, ground always from the bottom. Okay? If you draw this kind of a systematic circuit, make it easier for people to read your circuit. Okay, I've seen people draw circuit, input come from all over the place, you got to go and hunt, where is the input, all right? Okay? Okay, the other hint to understand circuit is that you need to recognize different blocks. Okay? Different building blocks. Okay? That's why in this course you will learn a lot of building blocks. Okay? All the way from part 1 to part 2. Okay, part 1 you have learned what kind of building blocks? You haven't learned it, okay? Alright, your op-amp, right? You learn the input pair, differential pair. Then you learn the current mirror load, right? Okay, then you learn about output stages, right? So those are circuit blocks that once you learn, you can recognize. Okay, that means now I give you a circuit, you go and hunt for this kind of circuit blocks. Okay, here is the input pair. Okay, here is the current mirror load. Here is the output stage. Okay, once you know this, the jigsaw puzzle will become easier to understand. Okay, and if the person draw the circuit properly, makes it your life even easier. Okay, so this circuit, okay, input is coming in here, output is here. Okay, now if you all finish part 1, you will learn that this is a amplifier stage. Okay, all right. How do we know? We see the differential pair. Okay, 2 input current source, tail current source. Okay, and then this is the current load, current mirror load. Okay, so this is a simple one-stage op-amp. Okay, which we use as a differential amplifier. Okay, so input is here, comparing with this reference. Okay, right? And then here is the output of the first stage, which is amplifying what is the input. Okay, and the amplifier, the first stage is GM times R0. Okay, GM of the input differential pair times whatever is the output impedance at this node here. Okay, so this will go into the second stage, which is the positive feedback stage. Okay, so basically it is you see this circuit? This is the first stage, your pre-amplifier. This is your positive feedback circuit. Okay? Okay? Pre-amplifier or differential stage, latch stage. Okay, so we come to this stage now. Now this one we look and we can see some old friends there, right? What do you see here? You see your cross couple, cross couple NMOS. You see your cross couple PMOS. Right? So this gives you a clue that this is a positive feedback already. Okay? But we see some additional devices. What do we see? We see these 2 devices and we see these 2 devices. Okay? Now, what are these devices for? We can ask ourselves. Alright? Okay, so this one, I think is quite obvious because it's taking the output from the previous stage. Okay? That means this output becomes the input of this stage now. Okay? Right? So the output becomes the input. Okay? How to shift the signal from here to here is through these two devices. Okay? What about these two devices here? What is it for? What do you think this is for? What is these two devices here thing? So actually these two devices, I can't even read what's the thing. So small. See whether I can zoom out a bit. TP6, TP5, and TN7 and TN8. What do you think these devices are doing? They are being driven by this signal, phi 1, which is basically a clock signal. Okay? So I give you a clue, right? Okay, this kind of a positive field comparator works in two phases, the track phase and the latch phase. Okay? The track phase means the pre-amplifier phase. Okay, that means my pre-amplifier is amplifying a little bit the input. Okay? The latch phase is my positive feedback phase. Okay, so it's a two-phase, okay? So what is the pre-amplifier phase or the track phase? Is when this signal is low. Okay? When phi 1 is low, what is happening to this latch circuit? Can you all see? When phi 1 is low, no current. Okay? What else? How about some friends on this side? A lot of input on this side. How about some input from this side? When phi 1 is low, what happened to the circuit? Phi 1 is low. This signal is low. What happened to this side? Sorry? QN. What's QN? Phi 1 is low, is zero, is ground. What happens to this circuit? When phi 1 is low or zero, what happened to these two devices? TN7 and TN8. What happened? This is low. What happened to these two NMOS? Off, right? Gate is grounded, right? So they're off, open. Okay, they're off. Okay, they're off means that these two nodes are separated from these two nodes. Because this switch is off. Okay? When phi 1 is low, what happened to TP5 and TP6? They are on, right? Okay, they are on. That means what happened to these two nodes? What's the voltage? They get pulled high, right? Alright? Okay? Alright? Alright, so you can see that when phi 1 equals 0 or the track phase, this part here is amplifying, okay, because this part here is independent of phi. There's no phi here, okay? And then this side here, what happens is that these two is off, this two is on, so these two is pulled to VDD, right? Because this is off, so what you say, there's no current coming down. So the top part and the bottom part is isolated, okay? All right? And then if you assume that these two voltages are high enough to turn this on, what it means that these two parts will be pulled to ground. Okay? So during the track phase, the two output is pulled to VDD, and the two output on the lower side will be pulled towards ground. Okay? During the track phase. Right? Okay, this is what I'm saying. And then we go from the track phase to the latch phase. It means now I make phi 1 equals 1 or high. Okay? Then what will happen? When phi 1 goes high, what happens to these two? They will turn on, right? They will turn on. What happens to these two? They will turn off. Okay? So now what happened to this circuit? I turn this on, that means current can flow down now, right? How much current will flow down will depend on what is the voltage difference between N5 and N6, which is the two input to the latch stage. Okay? So if this side is higher than this side, more current will come down. Right? More current will come down here compared to this. Okay? Right? So more current will come down means that what? Means what? Means that there will be positive feedback. Okay? And then the positive feedback will flip the two outputs. Okay? That means these two output now, initially when phi 1 equals 0, they are both at VDD. Alright? Now when I go to latch phase, one of them will get pulled lower and lower. Okay? And then it will flip like this. If the input difference is opposite, it will flip like this. Okay? Okay, and then this is just a driver inverter. This is just an inverter driver. Okay? When this voltage exceeds the switching threshold of the inverter, right, the inverter will just react. Okay? Alright? Okay, and then we have D1, D2 in the preamp just to limit the output swing. Okay? We should help the what we call as a recovery. That means when you want to make another comparison. Okay? Alright? So you can refer this. This was published in very long time ago, 1985. In 1985, maybe you're not even born yet, is it? In 1985. Okay? Alright, so this circuit was published by... Oh, okay, sorry, there's a typo here. It's supposed to be Yukawa, not Yubawa. Yukawa. Yukawa. Okay? Alright? Okay? Okay, so this is another example of a comparator with preamplifier and latch. Okay, I think why don't we take our break now? Alright, we can take our break now. Alright, and then we'll come back and discuss this after the break. Yeah, compared to the previous lectures, today is relatively less slides, okay? Okay. Maybe I ask any questions you have. You want to ask any questions? Okay, concept-wise, should be quite simple. What a comparator does. It's only how to make the comparator faster, and then how to make the offset smaller. This is what we'll discuss later on after the break. Okay. Okay. If there's no questions, then we can go for a break. Please come back at 7:45. Okay. And if you have any question, please you can approach me also. Okay. Any question before I continue? Okay. If not, let's go on to the second circuit taken from this paper by Yin. This is now. Okay, the first paper was when? 1985. Okay? Then 7 years later, this author Yin, okay, published a high-speed CMOS comparator, okay, with AB resolution. And this is the circuit, okay? Okay, by now you can understand the circuit, right? Or you can identify the main blocks in this circuit, right? By now you should, okay? Right? So what is this? What is this circuit? This is a preamplifier, right? Okay, except now you can see that it's a bit more tricky because the preamplifier input is here, but where is the preamplifier load? It is here now. Okay? So basically, they have shared the preamplifier load with the latch circuit. Okay? Alright? Okay? So preamplifier input, preamplifier load, okay, M4, M5, okay? And then here is this is a circuit that we should very familiar. This is the latch circuit now, except that you don't need the two input here because now preamplifier is connected directly to here, okay, right? So see here, it's preamplifier, right, has its own load, and then the load drive the input side of the latch circuit. Now he saved this, he also saved this, okay, right? Okay, because all the load for preamplifier is shared using these two. Add one more transistor M12 here, okay, and then the top half is exactly the same, right? The two NMOS driven by phi 1, the two PMOS driven by also phi 1, cross-coupled PMOS, okay, right? And then now add one more stage here. So this case was a simple inverter. Now put the SR latch, okay? Now, okay, we will go through this slowly one by one, okay? So here M4 and M5 are shared between the preamp and the latch. And what is the gain of the preamp now? Okay, what is the gain of the preamp? Okay, so basically you will see that GM input convert the current through GM, okay, and then this current come back to voltage through R on, okay, right? Kickback noise could be high. Why? Because these two nodes, this positive feedback, that means here and here there could be big positive feedback swing, which can couple to your input through any parasitic capacitance between gate to drain. Okay, all right. Okay, so during the two phase again, the preamp phase and the latch phase. Okay, so same as previously, phi 1 equals 0 is the track phase or the preamp phase, and now with additional signal here phi 2. Okay, so phi 1 must be 0, these two off, these two on. Phi 2 must be 1, which means this switch NMOS is on. This is the preamp phase. Okay, so like previously, these two, because these two is on, these two is off, this part top and bottom is decoupled, C and D will pull high. Okay, pull high. All right, and then when these two pull high, what happened to this SR latch? What's the property of SR latch? What's the property of SR latch? How does SR latch work? S and R inputs, 0, 1, the output will be a certain state, right? 1, 0, the output will be a certain stage. There will be an illegal state and there will be a holding state, right? Okay? So this SR latch is that when C and D are both high, what happens is in the holding state. That means this latch will hold the result from the previous comparison result. Okay? You contrast it with this previous circuit, the Yukawa circuit. Okay? What happened to the output? The output will not hold. Right? That means during the preamp stage, where these 2 point is pull high, this will automatically pull low. Right? So if the previous state was high, it's lost. It's gone already. Okay? Whereas this guy, during the track phase, when these two is pull high, this latch will hold the previous output. Okay? Alright? Until the new output comes in. So automatically it will hold. Okay, that means you have a change. The output will change, and then during the next track phase, this will not change. It will hold until the next latch phase. Then it will update. Okay, so this is the reason why you have a RS latch, okay, to hold the previous decision. Okay, and then you look at my notes here. I go in quite detail into how the different transistors are working, okay, during the latch and track phase. Okay, so during track phase, when this is off, this is pull high. What happens over here? This is on. So if there's any small current going through here, right? For example, this current coming down, part of it will go here, part of it will go across here to here. Okay? Alright? And these two imbalance, these two currents will cause an imbalance in these two voltages A and B during track phase. Okay, either A higher than B or B higher than A. Okay, depending on the input difference and depending on what's the difference in current coming down. Okay, so these two is used to set up the initial difference, small difference for the positive feedback. Okay. Okay, Okay, this is the third example of a comparator. Okay, so now you can see from a high level point of view, right? Here is your comparator. Okay, what is this to? Two-stage preamp. Okay, first preamp, second preamp. Okay, and then two-stage or latches, okay, followed by a last SR latch which you saw previously. Okay, so you see how the progression, the first paper Yukawa only got one preamp and one latch, one clock latch. Then the second paper by Yin, one preamp, one clock latch sharing the same load devices, and one SR latch. Now we come to this paper, 1999. They have two preamp, two different latch. One is clock, one is unclocked. Finally, the SR latch. Okay. So, what is the reason for all these changes? Can you think? Okay, so by having two preamp, basically you have higher gain, higher preamp gain, okay? Which means that you can be less susceptible to metastability, okay? Okay? And then the two latches basically is to speed up your positive regeneration, okay? And then the SR latch is just to hold the previous state, okay? Okay, so you can see, right? Not so clear, maybe expand a bit. Expand a bit. Okay, so the first preamp, okay, very standard, right? Is capacitor coupling, so you don't worry about the capacitor. It's simple NMOS differential pair, bias tail current, and the output is what? Output is a simple diode connected load, right? Diode connected load, right? Gate to drain, okay? Which you will learn in part 1 that what is the impedance at this node? It's 1 over GM. 1 over GM. Okay? Alright? Okay? So the gain of this stage is this GM of NMOS, we call GMN, multiply by the impedance, which is 1 over GMP. So the gain is basically GMN divided by GMP. Okay, right? Okay, which means that the gain is not so high, right? Right? Remember your op-amp gain was what? Was GM times R0, right? R0 was assumed to be big, okay? Now you have a very simple load, which means that your R0 is not so high, it's 1 over GM. Okay, that means the gain of one stage is limited already. That's why you need 2 stages, so that the gain is P1 times P2, okay? So this second stage, okay, looks similar and looks different. Okay, what is similar? 2 input NMOS differential pair is again here. Where's the tail current? Is here. Okay, at the bottom. Right? And then now you see some interesting circuit tricks here, okay? That means this tail current, during track phase, I turn this one on, turn this one off. Okay, so this becomes the tail current of the P2. Okay? So P2 now is almost the same as P1. Input, tail current, load, again 1 over GM. Okay? So now what is the gain of P1 and P2? GMN divided by GMP times this GMN divided by this GMP. Right? The GM is slightly different because this is 150, this is 100. Even though the dimension is the same, but the bias current is different. Okay? Alright, so interesting, You have a trick here, right? To share this tail current. Right? Track phase, current go this way, this is off. Okay? Now, during the track phase or the preamp phase, what happened over here? This is off, right? Track phase, L, this is low, so this is off. Okay? What happened to here? What happened to here now? Okay? This is off, and we are shorting these two through this transistor, right? Okay? And then these two is sharing here. Okay? Right? That means whatever is the output from track phase, alright, from the P2 output is put here, put across here. Okay? During track phase. Okay? So during track phase, P1 and P2 will generate a voltage difference, VOP, VON, and this voltage difference will be sitting here. Okay? This is off, so this is open circuit. Okay? Alright? Open circuit. Right? And then, when I go to the latch phase, which means now this goes 0, I turn this guy off, I turn this on, so this current will now pull current through here. Okay? And then as you pull current through here, depending on the voltage of this and this difference, right, will pull these two output nodes by positive feedback. Okay? Right? That means if this current here is higher than this current, so for this current to be higher means that this has to be higher than this. Okay? So this will go up, this will go down. Alright? And then as this goes up, it will pull even more current through here. So the positive feedback will take place. Okay? Okay? So previously they played a trick that they share the preamp load. Now in this circuit, they play the trick that they share the bias current here. Okay? Okay, so you can see two low gain preamp, P1, P2. Okay? And why you use two-stage? Because with this circuit, you can get a bigger bandwidth of the preamp, which makes the preamp faster. Okay? And then we have two stages. Remember, this one followed by another L2 here. Okay? We have two stages of regenerative latch. Okay? To reduce the metastability. Okay? Okay, so now we talk about one of the problems of the comparator is the offset voltage. Okay, because the offset will limit the ability of your comparator to compare the smallest difference, voltage difference. Okay, so why is it important to compare smaller voltage difference? Okay, so for example, in a SAR ADC, depending on number of bits, the more bits means that the LSB voltage is smaller and smaller. That means you want to compare, your comparator must be able to compare smaller and smaller differences. Okay, so that's the difference. If you have an 8-bit SAR ADC or you have a 10-bit SAR ADC, the performance of your comparator becomes very important. Okay. So with MOS analog circuits, one of the important advantage is that you can have capacitors, and if you have capacitors, it means that you can store and cancel things. Okay, all right. So the idea of this offset cancellation is very simple. Okay, we just want to store whatever is offset onto a capacitor, and then we just cancel it. Okay. Okay, how is this done? Okay, very interesting, huh? First, we talk about cancellation at the input side. Okay, so for example, okay, we look at this comparator. Okay, let's say we use the op-amp as a comparator. Okay. Then what happens? Okay, so this is the op-amp. We use a comparator. One side we connect to ground. All right. Input is here. All right. Okay, so during the very first phase, which we will call the offset storage phase. Okay, that means when phi 1 equals to 1. Okay, it means I close this switch. Now, what happens? I close this switch. It means I also close this switch, and this is open. Okay, that means I have a circuit look like this, right? I close this, output connect to here. I close this, here connect to ground. Okay, and then I say, okay, now if my op-amp has an offset, okay, which we model here, Here the offset is not shown here. Now the offset is shown here. Okay, what will happen? Okay, so if you analyze this circuit, you'll see that what is the voltage stored across the capacitor? It is PC equals to offset voltage times this term. Okay, A divided by 1 plus A. Okay. So what is the value of VC? What is the value of VC? If A is very big, what's the value of VC? VC will be the offset, right? Right? A very big, that means A divided by 1 plus A will be approximately A divided by A will be 1. Okay? Okay, so, which means that, you store the offset across the capacitor. Right? Then now, when I want to do the actual comparison, I open phi 1, close phi 2. I get this. Okay? Right? And now, what is the voltage across my comparator input now? Okay? It will be V in, and then plus VC, right? V in plus VC, right? And then subtract from VOS. Okay? Alright? Or, if you look at it from here, okay, from this, since this is the positive input, right? This value is VOS. Right? And what is this value? This value here is V in plus VC, which is V in plus what? Plus A01 over A VOS. Okay? Right? Okay? So now I open up the bracket and you solve it, you find that the difference is the effective offset has been reduced by 1 plus A. Okay? Right? So if I make A as big as possible, I will get better and better offset cancellation. Okay? Right? Of course, in this world, there's no free lunch. Alright, in this world, there's no free lunch. Okay, that's not true. In the university, there's a lot of free lunches. Is it correct? Huh? No free lunch in the university? No, I thought the university got a lot of events, right? A lot of events. When they have a lot of events, then they have a lot of food. Then, okay, last time, now COVID, no more. Okay, but before COVID, the university got a lot of events, a lot of seminar, all this, right? They always cater food, right? Right? And then there's always more than enough food for students to go by and eat also. It's not true? It's true what? When I was a student, it was true what? Huh? When I go and visit my friend, there's one year I visit my friend in Berkeley. He said, come, let's have a free lunch. I said, what free lunch? Oh, come, there's a seminar outside this lecture theatre. There's free food there. You just go there and eat. Okay? Okay, but there's a price we need to pay. Okay, so in the real world, there's always complications. Okay, so this scheme works very well. Okay, in concept, I store the offset, right, and then I use the VC to cancel my offset. Okay, very good, right? Very nice and pretty. Okay, what is the limitation? The limitation is we are using switches. Remember all these switches? Okay, right? We are using switch to store, switch to open and close, on and off. Okay? So, I think we talked about this previously, right? The switch is a MOS device. MOS device has a channel. The channel has certain charges. Okay? When it's on, when you turn it off, the channel goes away. The charges has to go someplace. Okay? The charges cannot disappear. Right? So the charges, when the switch is turned off, there's something which we call charge injection. That means the charge has to be injected out of the channel. Alright? Outside of the switch. Both sides, source and drain. Okay? And so because of this charge that's injected out, some of it is injected into your capacitor. Right? And this will cause a error in what is the voltage that's sampled across the capacitor. Okay? Alright? Okay, so here it is. Okay? This is the effective offset after you do all this thing. Previously, we say that it is VOS divided by 1 plus A, right? But because of the charge injection, okay, if you say that there's some charge, delta Q, that's injected also into the capacitor, it will cause a voltage error of delta Q over C. Okay, remember the capacitor definition is C is equal to what? C equals to Q over V. So V is equal to Q divided by C. So now I've injected some charge into the capacitor, which will cause a small area voltage delta Q over C. Okay? And what is this? What is this? What is this? VOSL divided by A. Remember, this is only your preamp. Okay? This is only your preamplifier. You connect it to a latch, a positive feedback latch. This positive feedback latch also got offset, you know? Right? This positive feedback also got offset. Because this positive feedback latch also got mismatch. Right? So this latch also got offset. And this offset, when you refer back to the input, you just divide by the preamp gate. Okay? You'll be surprised, this latch offset can be quite high, you know. Right? So if you don't believe me, alright, you can run some spice simulation. Okay, that means you build a latch, the latch cross couple, right? Cross couple, PMOS, NMOS, Okay, and then you put identical device, but then because of mismatch, they are not really balanced. Okay? So one way is you can just model it by putting a same device, then put a small voltage source to model the offset. Okay? And then you will see, right? With this small offset between the two PMOS on top, two MOS at the bottom, what is the offset of your latch circuit? Okay? Okay. Are you all familiar with offset? How to simulate offset? How do you simulate offset? Mismatch. Or how do you simulate mismatch? You know? Sorry? Okay. In simulation, right? Because your devices have mismatch, so it will cause offset, in the op amp, whatever, right? And how do you simulate this? Okay, have you all done this before? Okay, so basically, it's quite interesting. Is that the simulator is quite powerful nowadays, so you can actually do what they call Monte Carlo. Monte Carlo means that even though you put the same device into the schematic, the simulator would create small differences in the model M1, M2. M1, M2 input pair, right? Right? It's exactly the same, right? But then, when you want to simulate a mismatch, you know that they are slightly unbalanced. So the simulator, when you run the Monte Carlo, would change some parameters, right, to model this imbalance. Okay, and then you can see the offset. Okay, Monte Carlo, you know, right? Monte Carlo, you know where Monte Carlo come from, right? Gambling, Monte Carlo. Okay, statistical, right? Okay, right? Yeah. So that is how you would do it using cadence, You run a Monte Carlo, and the Monte Carlo will be many runs. Okay, because you want to have statistics. So Monte Carlo could be 100 runs. Okay, and for each run, the simulator would randomize a few parameters. Okay, so we simulate 100 runs, 200 runs. Then you can see the Gaussian. Let's say the offset will be a Gaussian. Okay, with a 1 sigma, right, value, all this. Okay, so it needs a lot of simulation time to run. Okay, so the cheap and dirty way is you just don't run Monte Carlo, you just put a voltage source there. Okay, you say, okay, now I think there's a 10 millivolt offset between M1 and M2, so I put a 10 millivolt voltage source in the M1 gate or whatever, all right, to model the offset. Okay? Okay. Okay, so previously we talked about we use a capacitor to store the offset at the input side. All right? But we can also store the offset at the output side. Okay? So this is how you do it. Okay? This is your comparator again. Now my capacitor I put at the output. Okay? So now, during the storage phase, phi 1 equals to 1. Okay, I will close this switch, open this one. That means I don't connect, open circuit the input, connect the this input to ground. Alright? And then connect this capacitor to ground also. Alright? And then if there's an offset here, this offset will be stored in VC. Okay? Right? So quite obvious, right? This voltage should be what? Voltage difference will be VOS times A lah. Right? So VC is basically A times VOS. Okay? Okay? So offset stored on capacitor C. And then during the actual comparison phase, I just connect back the input. Alright? I take the output from here. Okay? So you can see, so this output will be whatever is the input minus the offset, and then I subtract out the offset. Okay? Alright? Okay, so the good thing about this scheme is that you will cancel out the offset. Okay, and you don't need a very high gain. Okay, right? Okay, but same thing again, because you have switches and everything, you have additional small error due to charge injection again. Okay, right? But the good thing about this is that the charge injection happened over here, right? And therefore, when you refer it back to the input, you divide by A. Okay, so the input referred error is small. Okay? Okay, the charge injection always happen at the end of your storage. Yeah. Okay, so for example, this is the input offset cancellation, right? Here, during phi 1 equals 1, this is where you store the offset here, right? The VC equals to this. Right? So during this phi 1 equals to 1, this is where I store the offset across C as VC. Right? So far, so good. Now, before I do the comparison, what I do is I have to open this switch. Right? I have to open this switch. I have to open this switch. Right? This switch was closed when I was storing, and now I have to open. When I open, this is where the charge is injected. Okay? Alright? When I open the switch, charge is injected. So when I open and charge injected, that means I change the storage VC a little bit. Okay? Okay, so same thing here lah. Alright? When I close this switch, I'm storing the offset VC across here. Alright? And then when I do the comparison, I have to open. I have to open this switch. When I open, once again I inject charge. Okay? Inject charge, I will change slightly what I store here. Okay? Alright? The difference of course is now I inject charge, I change this voltage, but this is at the output. So when I refer to the input, I divide by A. Okay? The other one is I'm at the input already, so no more divide by A. I'm already at the input. Here I'm at the output. Okay? Okay. So here is one example. Okay, or two examples by the same author Dingwall. This circuit in 1979, this circuit 6 years later in 1985. Okay? So you can see here, right? Here, what is going on here? What circuit is this? What circuit is this? Inverter, anybody else? Inverter, right? Simple circuit inverter, right? Okay, why inverter can be used as a free amplifier? Inverter is a digital circuit or analog circuit? Okay, who says inverter is digital circuit? Raise your hand. Nobody. Inverter is not a digital circuit. Inverter is digital circuit, right? Yeah, so inverter can be both a digital or analog circuit depending on how you look at it. Okay? If you just look at it from 1 and 0 point of view, of course it's a digital circuit. Right? If you want to look at it, how the transfer curve from input to output, okay, is an analog circuit. Actually all circuits are analog. Actually all circuits are analog, okay? Okay, digital is just an abstraction. Okay? So how can the inverter be used as an amplifier? Must think, how can I use the inverter as an amplifier? Huh? Okay, why both must be in saturation? Okay, we can look at it from the transfer curve point of view, right? That's easier. Okay, how does the transfer curve inverter look like? Output, input, how does it look like? Input is low, output is what? High, right? Input is high, output is, how about in between? So there's a slope, right? There's a slope, right? There's a certain slope, right? And this slope is what we call the high gain part, right? And that's what you need for amplifier, right? You need a high gain. You cannot use it at the two side where it's flat, right? Because there's no gain, right? But you can use it during the transition where there's a gain. Okay? So now the question is, how do you use it in the high gain region? Okay, how do you use the inverter as an amplifier in the high gain region? Right? This is an important question, right? Okay, so you can see in this circuit, the clue is this switch here. What is this switch doing? What is this switch doing? Huh? Look at it. What is this switch doing? When this switch is on, what happens? Huh? Okay, don't worry. Now I ask you, when this switch is on, what happened to the inverter? I connect the output to the input. What happens when I do that? Okay, of course I shorted. Of course I shorted lah. Diode, okay. Okay, how about you think of the transfer curve now, right? We know transfer curve like this, right? Okay, now I short the input to output. How do I find where on the transfer curve I'm operating? Huh? In the middle. Okay, how do you find a point first? How do you find a point? You have output curve like this. Now I connect the input to the output. How do I find where am I operating in this transfer curve? I must be operating somewhere, right? Right, the operating point must be on this curve. Now the question is where in this curve? I just draw output equals input. I draw another line up, right? So I have two lines. I have the transfer curve of the inverter. I have another line which input equals output, right? And where the thing crosses is where is the operating point, right? And most of the time it will cross at the high gain region, right? You don't believe, you draw lah, you don't go and draw it, okay? All right. So now we understand what is this switch for, right? Okay, so to use the inverter amplifier, we have to set up the operating point correctly, all right? And this switch is for that. When I close this switch, I connect input to output. I will bias this inverter in the right high gain region. Okay, which allows me to use it as an amplifier, because then now I can inject input through the capacitor onto this point. All right, and if this is high, you amplify. Inverter amplify opposite, is a negative slope down, right? So input goes high, output will go low. Right? Okay, it's not the normal amplifier that goes this way, right? Okay? Okay. So here is the offset cancellation at the input side. C is at the input side. Okay? Now, for the inverter, what are we talking about? What is the offset as amplifier? What are we talking about now? What offset are we talking about? Now, this inverter only got one input, right? Only one input, right? Okay, so what is the offset we're talking about? Okay. So actually look at this circuit, Here is your two inputs, right? Your two comparator input, right? One input here, the reference input here. Okay? So now, let me just expand this a little bit so I can also see clearly, right? During the offset storage phase, right? During the offset storage phase, what we are doing is phi equals high, I close this switch, right? Connect input to output, right? At the same time, this is closed, phi equals high, right? I close this switch. So what is stored across this capacitor is the high gain voltage of the inverter on this side, the reference on this side. Okay? Right? Okay, so here I'm biasing the inverter in the high gain region. Right? And here I'm storing the reference across this capacitor. Okay? Then when I want to do the comparison, I'm opening phi 1, this phi equals 0. I make this 0, open this switch. I open this TG1 switch, and I close this TG3 switch. Okay, phi equals 0, phi bar equals high. Okay? Right? So now, what will be this voltage? This voltage will be input, and here if this is plus minus whatever was stored here. Okay, whatever was stored here. Okay? Input, and whatever was stored here was reference minus the passing point. Okay, that means once I put it across here, then input minus this voltage minus reference, okay, and the reference point, and then the inverter will just do the amplifying. Okay? Alright? So in this case, what we call the offset of the inverter actually is the operating point of the inverter. Okay? So you know that this inverter, this transfer curve is changing, right? It's changing for different inverter. I put one inverter here, I put one inverter here. Same inverter, I put 3 points. But if you measure the transfer curve, they are not exactly the same. Right? Because of mismatch and everything, the curve is shifting a little bit. Okay? So it looks like equivalent offset. Okay? Looks like equivalent offset. Okay? So if there's nothing you learn from this course, you just learn that every transistor is different. Okay? Every transistor is different, okay? They're not exactly the same. Alright? This reminds me of a joke. So when I think one of the courses I took was high frequency lab course, right? Where professor asked us to do a lot of measurements, high frequency measurements using S parameter or that. At the end of the course, the professor asked us, okay, what have you guys learned from this lab? Then all of us, including me, we said, but what we learned is this. Okay, a capacitor is not a capacitor. Okay, An inductor is not inductor, a resistor is not resistor. Why do you say that? Because we found that when you measure at high frequency, right, the capacitor actually has some inductance. You know, right? The inductor actually has some resistance. Right? So at high frequency especially, you see the effect very clearly. Right? The capacitor ideal curve is what? In the frequency domain is coming down, right? It's 1 over S, right? Right? But because you see that there's resistance, all this, the curve actually will change shape. Right? And you may not understand why until you realize that actually in the capacitor there's a small piece of wire which actually is an inductance at very high frequency. Right? So you can see. That's why interesting when you see this kind of schematic. Have you seen a PCB schematic? They put a 0.1 microfarad capacitor, they put it in parallel with a 10 microfarad capacitor in parallel. Right? So you may ask the question, why they do this? Right? Why don't you just put one capacitor there? Right? But because of the high frequency characteristic is different. The 0.1 high frequency characteristic is different from the 1 microfarad. So you put in parallel, you get a composite effect. Okay, so that's the reason. Okay, so here basically is, so you can see, and then their next version is just put 2 in cascade lah. Okay, the gain for 1 is not enough, put the second one. Okay, all right. So it's exactly the same, right? So here just now, this was the previous version. Now they just add one more. Okay, and when they add one more, it's also once again store the equivalent offset on this capacitor. Okay, all right. Okay, one more example of a circuit. Okay, I have 2 preamp, P1, P2, okay? 2 preamp stages, okay? And now, what am I doing? Even though I have 2 preamp, I use only 1 storage capacitor at the input here. Okay? So now the signaling concept is a bit different. We call this storage signal the AZ signal, auto zero. Okay, auto zero means I'm storing the offset. Okay, all right. So now, if you just take the half circuit, okay, this kind of circuit is what we call the fully differential circuit. Okay, 2 input, 2 output. Okay, fully differential. Okay, previously all the circuits you saw was mainly 2 input, 1 output. Okay, all right. We call this the single-ended. Right. Here now, this circuit and some amplifiers that you will work with are also all fully differential. 2 input, 2 output. Okay, what's the reason for this kind of circuit? Anybody know the answer? What is the advantage if we use a fully differential circuit? Anybody can guess? Huh? No? No what load? No information load. What do you mean? what do you mean? Okay, if you read all the papers right now, all the advanced papers, they are all using fully differential circuits. Okay, the reason very simple, all right, is that in your chip now, if there's a lot of noise, in your chip circuit, right, the noise will be in both outputs. So if I take the difference, I can reject the noise. Right? If I have 2 output, if I only got 1 output, I can't tell the difference because if I only got 1 output, that means my other reference is ground or something. So if there's any noise here, right, it's going to make my output quality bad. Okay? But if a differential, I can treat it as a common noise. Okay? Right? Okay? So this applies to both input output also. That's why we take a differential input, because any noise that's common will be rejected. Okay? Okay, so with this, you can see that what is taught across here is also once again the offset. Okay? Alright? And then if we assume that the 2 gain is high, the offset will roughly cancel. Alright? Okay? Okay, things are getting more and more complicated now. Okay, the circuit is looking more and more complicated, but always the concept is always the same. Alright? We are trying to store some offset information onto capacitors, and then so that we can get the effective offset to be lower, right? Using this storage concept. Okay, so here now, this is 1992, proposed by Razavi. You all know who Razavi is? Who is Razavi? Okay, he's a professor at where? UCLA, right? UCLA, right? Okay. Actually, I saw Razavi many years ago when he was a student. Okay, he was a student. Okay. Anyway, okay. So you see this circuit. There's storage on C1 and C2. Okay, C1 and C2. Okay, but this circuit, as drawn here, is not working very well in practice. Okay, why? Because C1 and C2 is loading the output here, and therefore the speed is reduced. Okay, you need time to go and charge these 2 capacitors. Okay, then during positive feedback, okay, GM2 is still inside. Okay, and therefore it may cause some stability problem, oscillation. Alright, and then finally you have S5 and S6 here. When they open, they are also injecting charge injection during positive feedback, okay, which may cause problems. Okay, you see here is where the positive feedback is. You see, input positive, output positive, input negative, output negative. This is the positive feedback connection. Okay, here is negative feedback, right? Plus, minus, minus, plus. Okay, if you want to see the full detail, just read. Just read, read some of the notes I put here. Okay. Okay. So in order to solve all this problem, okay, a few things we do. One, the loading problem, we add a buffer to isolate this capacitor from this preamp during the loading or storage phase. Okay, that's why it's B1, B2. Okay, isolate C1, C2 from A and B. Okay, and then we put additional switches S7, S7, S8, S9, S10. Okay, to disable the positive feedback. Okay, when we are opening S5 and S6. Okay. Okay, so if you don't believe me, just go through the circuit. Okay, during the offset sampling phase, during the tracking phase, and then during the regeneration phase. So you can see that there are 3 phases there. Okay, first phase is we store offset on C1, C2. Okay, second phase is when we do the tracking phase and the offset cancellation phase, and then here is the third phase when we do the final positive feedback phase. Okay. Okay, another circuit, okay? Here also, they call it offset calibration, which is cancelling the offset, okay? All right? So you see here, the original offset distribution is plus minus 50 microvolt, okay? After you do the calibration offset cancellation, you bring it down to plus minus 3 microvolt, okay? So almost better than 90% cancellation, okay? Right? But it's the same thing, okay? It's the same concept, all right? Except that here you have a calibration circuit, okay? You have a SAR ADC inside, okay? You have logic, okay? You take the output, you low pass filter, all right? And then you apply calibration, okay? So you know offset. What is the cause of offset? Offset is caused by mismatch, all right? For example, in your input pair, okay, how do you calibrate it out? Instead of storage, how do you calibrate? You change the current in the input pair, right? See, offset is defined to be what is the offset, what is the input difference when the current is balanced, right? Right? Okay, so for the input pair, right, offset is defined to be if I balance the two currents, what is the difference in the input voltages? Okay? So one way to correct it is now I don't balance the two current. I imbalance the two current and make the input voltage the same. Okay, so that's a different way to look at it. Right? Okay? So if a circuit without mismatch, I balance the two currents, the voltage will be balanced. Correct? That is zero offset. Now, if my circuit got mismatch and offset, it means I balance the two current, but the voltage input is different. So that difference is the offset. Alright? So now in calibration, I imbalance the current to make the voltage the same again. Okay? Right? So this is what it's doing here, okay? You can see, right? This is where they are injecting different current, imbalancing the currents. Okay? Okay, so in summary, alright, for the comparator, there are some non-ideal properties, okay, meaning the finite gain, the offset, the hysteresis, and the slew rate limit, okay? This one we know, this one we can either cancel or calibrate. This one is part of your design, okay, part of your design. That means you want to have hysteresis, you have to add some positive feedback in your preamp circuit. Okay? So your normal preamp circuit, right? If you just put a normal current source load or direct connected 1 volt GM load, there is no hysteresis. Okay? But if you add a cross-coupled positive feedback load, okay, you will get some hysteresis. Okay, but you have to be very, very careful. You cannot put too much positive feedback because the whole thing will not work. Okay, so you can add a little bit of positive feedback to give you the hysteresis. Okay, slew rate is because of the finite output current you have. All right, and then we talk about the settling behavior of the op-amp comparator. Okay, the linear settling, which is due to the single pole bandwidth, right? And the non-linear settling due to what? Non-linear settling is due to what? Due to the slewing, okay? Slewing, right? So the linear settling means a nice exponential settling, okay? The non-linear settling means once you have a finite slew rate, it cannot be a nice, right? Because it's limited by this slope, okay? This is what we call the non-linear settling, okay? Okay, then we talk about using positive feedback, okay? Using positive feedback to help us in our comparator, right? Which means we have a preamplifier and we add a positive feedback or regenerative latch, okay? Now, once we add positive feedback, what happened to the settling? What happened to the settling? You have additional exponential settling, okay, due to the positive feedback, okay? Okay, and then in one slide, we can see how we can calculate the positive feedback exponential settling, right? You have the two small signal circuit, Vx, Vy, and you can derive the output of Vx minus Vy, which will be a property of the initial difference plus the exponential settling, okay, due to the positive feedback, okay? That's what we mean by calculation of latch time. And then we also know that this latch type comparator, there's a potential method stability problem because the speed of the latch comparator depends on the initial difference. Okay, the smaller the initial difference, the longer it takes for the latch to settle at the high and low. Okay, so if the time is too long, we call it method stability because we can't tell. We can't tell whether the output is high or low. Okay, and we talk about how to solve this method stability problem. Right, one is to make the initial difference bigger so that the output will settle faster. All right. The other way is to reduce some of the parameters, right? Because the initial output depends on CL, depends on GM, right? So you can tweak it, all right, to make the initial thing higher. Okay, and then for this kind of, even though we use positive feedback, we still need a preamplifier to generate the initial difference. Okay, so for the preamp, okay, our design consideration is what is the gain and what is the bandwidth. Okay, and you know that there's a trade-off here, right? In op-amp design, right? You want high gain, your bandwidth normally is small, right? You want high bandwidth, normally your gain is low. Okay, so there's a trade-off. That's why sometimes you need low gain, high bandwidth, but we put more stages. We put, instead of 1, we put 2. All right? So we get, the gain is P1 times P2. All right? And then the other problem we found with this positive feedback is this problem. This problem called kickback noise. Okay? Kickback noise. That means because the output is being positive feedback and being flipped very fast, some of this transition can couple back into your input side, okay, depending on the coupling capacitance inside. Okay, and remember, your comparator, one of the input could be a reference circuit, could be a band gap circuit or whatever, right? So if some noise kick back into this, depending on how fast this circuit can recover, okay, right, it may cause problem for you. All right. Okay, then we talk about, okay, how can we sort of cancel or minimize the offset of your preamplifier circuit, okay, right? You can store the input, store the output, okay, or you can calibrate it, all right? So there are many circuits here that talk about it, okay? Quite a few talk about how to store the offset in capacitors, okay, and one more, last paper talk about how can you calibrate the offset out, okay? Okay, I think that's today. That's today's lecture on comparators. Hopefully, it's simple concept to understand. All right, but there's a lot of tricks and improvement to implement, right? On how to build a very high performance comparator. Okay. I've not decided on your project for this semester yet, so we have to see. Okay, just to understand. How many of you now know how to run SPICE simulation? Huh? On Cadence, on the Cadence machine in the huh? Sorry? No. I think we are trying to move everybody towards Cadence now. Okay? Reason very simple, right? Because Cadence is the main design software that's being used in the industry. Alright, so if you learn how to use Cadence here, next time you will go out and find a job much easier because you already know the software. Alright, LT Spice I think is not widely used nowadays. In fact LT no longer exists, the company no longer exists. Okay, because it's bought by ADI. Okay, alright. So the history, last time when there's linear technology, LT linear technology, they used LT Spice for their circuit design, but then the layout they still have to use Cadence. So Cadence is an integrated software platform. Okay, you do your design, schematic, simulation, everything. Then you can do your layout, and then you can check your layout for your schematic. So everything is integrated. Only thing is I got to pay money Okay. Okay. So how many of you here know how to use Cadence? Okay. How many don't know how to use? Haven't tried it? Okay. So that was the purpose of the workshop which Professor Heng wants to conduct. I think he will still conduct when he comes back. Okay. All right. So now the thing is that still not confirmed when he's coming back. Right. So this is the only unknown, and we actually need it for the project Okay. So if I assign the project now, not all of you can start because you may not know how to use Cadence. Okay. Professor Heng actually sent out the slide, right? So can you all try to see whether you use a slide to log on and try? That means basically you need to know how to get into the Cadence system. Okay, open the window or all the libraries, and then you need to learn how to draw a schematic. Okay, put in all the transistor, connect all the wire, all right, and then you need to know how to run a simulation. Okay, from the Cadence side. Okay, and then see the output waveform. Okay, that is the basic flow. All right, so it's similar to LT Spice. Same thing you're doing, right? Draw the schematic, connect all the wire. When you finish everything, generate a net list. Net list is just a description of your circuit, and then run the simulation. That means define what is your stimulus, what is your voltage, right? And then define what is the waveform you want to see, what is the analysis you want to do, small signal, transient, or DC, all right? And then how to see the output. Okay? So please give it a try, and then let me know. Okay? Then I can decide together with Professor Heng when he wants to hold the workshop, and when we can assign the project. Okay? Because this is the important part of this class is for you to learn how to actually use the Cadence software, right, to do your design, run your simulation, look at the result. Okay? This part is a very big learning part. Right, and this part cannot be covered in the final exam. Okay? Alright? Okay? So this is what you have to do and learn. Okay? Right? So please give it a shot and then let me know. Let me know your feedback. Right? Because otherwise you can't really do the project. LT Spice, you all know how to use that? LT Spice? Oh, it's the same situation. Okay, I think it's better. I think the whole direction is to go towards Cadence. Alright? But you have to use the workstation in the engineering side. Okay? There are some designated workstations. Okay, you cannot download into your computer. Now this software is licensed software, cannot, right? And please also, Professor Heng asked me to remind you, please do not download any pirated software, okay? Or use any pirated software, because the university is very strict about this. Okay? Because if the university gets complained or get wind of the fact that you are using pirated software, it can be very serious. Okay? So please do not download pirated software to use, okay? Cadence software, please, you all can set up an account with the workstations, alright? I think it's in the place is what they call EIT, is it EIT, right? Yeah. Okay, so first thing, know how to request for account. Okay, and then we set up for you. And then once you set up, I think we can quickly have the workshop to let you all know how to start using it. Okay, it's not very complicated. Open Cadence, open the window, all right, and then pick library, how to build a schematic, and that's it. Okay, all right. Okay, any final questions? Okay, otherwise, happy Valentine's Day, whatever is left. Okay, still got 3 hours. Okay, if you have any questions, you can come and see me here, or you can send me email. Okay, I will consolidate, then I will put the answers there.